Well, greetings to the Anglican Church's climate change action group and to the delegates and audience at this function on the 1st of September. I was very pleased and honoured to be invited to speak at this gathering as the topic of the conversation is an extremely important one. My name's James Renwick. I'm a lecturer in physical geography at Victoria University. My specialty is in climate variability and climate change. I'm very well aware of the international scene as far as the science community goes with understanding of climate change and the level of certainty we have about the basic facts around climate change. Almost all practicing scientists who are working in the area understand that greenhouse gas concentrations in the atmosphere, primarily carbon dioxide, are driving the changes in climate that we're seeing at the moment. And if we want to contain climate change to some hopefully manageable level, such as 2 degrees of warming globally, then we have to take pretty urgent action. Carbon dioxide concentrations in the atmosphere are already at about 400 parts per million, which is 40% above what they were for many thousands of years before the advent of industrial society. And they're on track to be double what they were pre-industrially within a few decades. And that sort of level of carbon dioxide in the atmosphere, if we look back to the past, has been associated with much higher temperatures than we've experienced really since civilization began, and quite a different climate. There are really only 3 ways to change the surface temperature, the average surface temperature of the planet. One is to change how bright the sun is. If the sun becomes brighter, more energy coming in, things warm up. If the sun dims, vice versa, it cools down. Or we could change the amount of that sunlight that is reflected away from Earth. So if there were more clouds or more ice, say, if the planet was whiter, we would reflect more sunlight, so less would get through to the surface and it would be cooler, and so on. The third way we can affect surface temperatures is through changing the amount of greenhouse gases in the atmosphere. And this is important because the balance of energy at the surface of the Earth is a balance between incoming sunlight, incoming infrared heat radiation from the atmosphere, and outgoing heat radiation from the surface. And it's because we've got that downward component of heat from the atmosphere because of the greenhouse gases that the surface temperature is higher than it would be otherwise. If we didn't have any greenhouse gases in the atmosphere, it's quite easy to estimate that the surface temperature would be around minus 18 degrees C. With the level of greenhouse gases that we've had up until recently, the surface temperature of the Earth is actually around plus 14 or 15. So it's over 30 degrees C different because we've got this fraction of 1% of the atmosphere that is sensitive to absorption and re-radiation of this heat. We know that carbon dioxide, a certain fraction of it does react out, get absorbed into the ocean and so on over a few years, but there's a substantial fraction that actually remains in the atmosphere for thousands of years. So how much carbon dioxide we put in the air now is critically important for a very long time. The other main human emitted greenhouse gases, methane and nitrous oxide, which are more potent greenhouse gases on a per molecule basis, but they stay in the atmosphere for a much shorter time. We're talking a decade or a few decades at most. Still significant, but not as important as carbon dioxide. And the other main one, which is actually the strongest greenhouse gas in terms of absorbing heat, is water vapour. What makes up clouds, what comes from evaporation from the ocean surface. The thing about water vapour is that it's only ever a response. It's a slave to temperature. You raise the temperature of the air, it can hold more water vapour. You lower the temperature and water vapour decreases, falls out, it rains. So water vapour only stays in the atmosphere for a matter of days, and it only responds to temperature. You cannot add water vapour to the atmosphere and have it warm up. It just doesn't work that way. It would just fall out as rain again. Now, we've had good measurements of carbon dioxide concentrations in the atmosphere over the last 50 or so years, primarily from the Mauna Loa Observatory in Hawaii. That was the first one established in the 1950s. We've had very good measurements at the mouth of Wellington Harbour, Bering Head, in Tasmania, South Pole, and so on. So a number of sites around the world, and they all tell the same story, that carbon dioxide concentrations have been increasing steadily since we started taking measurements, and those concentrations are now up around 400 parts per million. If you look at a graph, things are going up. It doesn't look that dramatic, but if you look back using ice cores and the bubbles of air that are held in those, going back over thousands of years, it's very clear that what's happened lately is dramatic. Carbon dioxide concentrations were pretty much static at around 280, 270 parts per million for thousands of years up until about the 1700s. And the change since then, when you plot it on the longer timescale, is just exponential. It's looking back again at the ice cores, we can see that over time through the ice ages, the last million years or so, carbon dioxide concentrations have gone up and down, typically between about 180 and 280 parts per million. And temperatures globally have gone up and down very much in lockstep with the carbon dioxide concentration. So looking at what's been happening lately, we can look at global consumption of coal and oil, gas, burning of fossil fuels essentially, to see how much should have been going into the atmosphere. We can estimate how much gets absorbed by the oceans and so on, and the numbers essentially add up. We can look directly at consumption of coal and oil and work out that the amount of carbon dioxide that would be released from burning those fuels would give us a certain amount of increase in the atmosphere, which matches what we observe. This is not new science that's just come along with the IPCC. The first scientific investigations actually occurred about 200 years ago, when people started to realise that there had been ice ages. They wanted to understand how this was occurring. And one of the first people to look into this was the famous French scientist and mathematician Joseph Fourier. He worked out that if there was no atmosphere, the surface temperature of the Earth should be about that -18, and he knew that it was a lot warmer than that, and thought it has to be the atmosphere doing something to cause that temperature rise. Tyndall, an Irish scientist in the 1860s, did some of the first lab experiments to show that it was the presence of carbon dioxide and water vapour primarily in the atmosphere that absorbed infrared heat radiated up from the Earth and then radiated it back down to the planet. So that was in the 1860s. By about the end of the 19th century, Arrhenius, a Swedish chemist, wrote one of the first papers where he did a calculation thinking about what if we increased the amount of carbon dioxide in the atmosphere. And he calculated that if we doubled the amount of carbon dioxide, we might see a global warming of something like 5 degrees on average. He thought this would take 1,000 years or more, based on where things were at in the 1890s with industrial use of coal and so on. And then coming into the 20th century, one of the key pieces of information actually came from Wellington. Athol Rafter, who ran a lab for the DSIR in Lower Hutt, and there's now a laboratory named after him, the Rafter Laboratory. He was one of the first people to notice this thing about the chemical signature of the carbon in the atmosphere and how the atmospheric carbon was getting older. So it must be the burning of fossil fuels that's related to this increase in CO2 in the atmosphere. We now estimate that a doubling of carbon dioxide concentrations will happen this century, by the second half of the century, not in 1,000 years as Arrhenius thought. And the other thing we've come to understand recently is that the carbon dioxide that we put in the air now, a good fraction of it stays there for a very long time, thousands of years. And the climate system takes hundreds to thousands of years to adjust to all this change in heating. It's really important to realise that the oceans both hold most of the heat in the climate system, but also they're absorbing most of the extra heat that's coming from the increase in carbon dioxide and other greenhouse gas concentrations. over 90% of the extra heating is going directly back into the oceans, which is a monolithic thing. It's very slow to change, and it's very slow to adjust to this huge increase in heating. The heat has to permeate down to the depths of the ocean, and the circulation of the oceans have to adjust globally, and this does take hundreds of years, if not 1,000 plus years. So that process will be ongoing for the foreseeable future. So where are we at in terms of action on climate change? Well, there was the meeting in Copenhagen, and there's been Cancun, Bali, the Framework Convention on Climate Change. The conferences of the parties meetings are happening on a regular basis, and there's the so-called Copenhagen Accord that most countries signed up to limit global warming to 2 degrees of rise, because that hopefully would avoid dangerous climate change. That's not a bad idea, but the catch is that no country is really doing anything that comes close to what's needed to actually achieve that target. It's been estimated by the Intergovernmental Panel on Climate Change reports that to actually be safely inside that 2 degree limit, we would need to reduce greenhouse gas emissions by up to about 40% by the end of this decade, 2020, and to reduce them by 80% or more by 2050. Whereas, for instance, the New Zealand government's just announced a 5% cut by 2020 rather than a 40% cut. So what's happening internationally with emissions? They're continuing to go up. It's very likely that, in fact, it's almost certain that that 2 degree limit will be exceeded, and a warming of more like 4 degrees is looking pretty likely this century. And that sort of warming would push us into a climate that we just haven't experienced before. We're just about at the limit of the emissions that we're seeing now, and starting to get into concentrations of CO2 in the atmosphere that would already push us beyond that 2 degree target. So even this decade, we really need to take significant action, not a 5% cut in emissions, but closer to a 50% cut in emissions as soon as we possibly can. I know it's a very hard problem from a technological and a political point of view, but it's an extremely urgent problem.